Section 1 Introduction. In this paper, we delve into the world of natural language processing, NLP, where significant advancements have been driven by large-scale pre-trained language models, LLMs, like OpenAI GPT, Flan T5, and Llama. These models are top performers in various NLP tasks. However, their large size can cause problems with computational efficiency and memory usage during the fine-tuning process. To address these issues, we've seen the rise of low-rank adaptation, LoRA, an efficient fine-tuning technique. LoRA works by keeping the base model parameters, the LLM, constant and training a smaller, additional module. This approach reduces memory and computational demands, making the training of LLMs faster. While previous research has focused on the efficiency gains provided by LoRA, there hasn't been much exploration into the inherent modularity and composability of LoRA modules. Typically, LoRA modules are trained to specialize in specific tasks and domains. However, the inherent modularity of LoRA modules raises an interesting question. Can we combine LoRA modules to efficiently tackle unseen tasks? In this paper, we explore the potential of LoRA modularity for broad task generalization. We go beyond training for a single task and carefully combine LoRA modules to perform well on unknown tasks. Importantly, our method automatically assembles LoRA modules, removing the need for manual design or expert knowledge. With just a few examples from new tasks, our approach can independently arrange compatible LoRA modules. We don't assume which LoRA modules trained on specific tasks can be combined, providing flexibility in merging any modules as long as they meet the specification. For example, using the same LLM. We call our approach LoraHub and our learning method LoraHub Learning. To test the effectiveness of our proposed methods, we use the widely recognized BBH benchmark with Flan T5 as the base LLM. The results highlight the effectiveness of combining LoRA modules for unfamiliar tasks through a few-shot LoraHub learning process. Notably, our method achieves a score that is comparable to the performance of few-shot, in-context learning. Moreover, our method significantly reduces the inference cost compared to in-context learning, removing the need for examples as inputs for the LLM. Our learning process is also notable for its computational efficiency. We use a gradient-free approach to obtain the coefficients of LoRA modules and only need a few inference steps for unseen tasks. For example, when applied to the BBH, our method can deliver excellent performance in less than a minute using a single A100. Importantly, LoraHub learning can be done with a CPU-only machine, as it only requires the ability to process LLM inference. With its flexibility and strong performance, our work lays the groundwork for a platform where users can easily share, access, and apply trained LoRA modules to new tasks. We envision this platform as a repository of reusable LoRA modules with a wide range of capabilities. This sets the stage for collaborative AI development, allowing the community to collectively enhance the capabilities of LLMs through dynamic LoRA composition. The ability to share and reuse modules ensures the optimal use of resources across various tasks. Section Summary. The introduction discusses the challenges posed by large-scale pre-trained language models, LLMs, in terms of computational efficiency and memory usage during fine-tuning. To address these challenges, the low-rank adaptation, LoRA, technique has emerged, which involves training a lightweight module while freezing the base LLM parameters. The paper proposes a method called LoraHub that leverages the modularity of LoRA modules for generalizing towards unseen tasks, allowing for automatic composition of compatible modules without human intervention. The results demonstrate the effectiveness of LoRA module composition in achieving high performance on unfamiliar tasks with reduced inference cost and computational efficiency. The authors envision LoraHub as a platform for sharing and applying trained LoRA modules, fostering cooperative AI development and optimal resource utilization. Section 2 Problem Statement. We're discussing large language models, or LLMs, which are typically based on a transformer architecture and have been trained on a vast amount of text data. These models can be structured in two ways, either as an encoder-decoder or as a decoder only. They can also be fine-tuned using large datasets that require the model to follow specific instructions, such as the Flan collection and prompt source. We're also considering the concept of cross-task generalization. This is when we have a number of different tasks, let's say n, that we'll call T1, T2, and so on, up to Tn. In real-world scenarios, users often want their LLM to be able to handle new tasks that it hasn't seen before. This ability is known as cross-task generalization. There are two main types of cross-task generalization: zero-shot learning, where the model doesn't need any examples of the new task, and few-shot learning, where the model needs a few examples to learn from. Our focus in this paper is on few-shot learning. So, If we have a new task, which we'll call T prime, that isn't in our original set of tasks, and we only have a limited number of examples, Q, for this task, our goal is to adjust our model, M theta, to get used to T prime using only these Q examples. One straightforward way to do this would be to fine-tune the weights of M theta based on Q, which would give us a new model, M phi, that performs better on T prime. However, this method is not very efficient, it takes a lot of time, and it's not very stable when Q is small. That's where LoRA tuning comes in. LoRA is a method for fine-tuning that's more efficient in terms of parameters. It allows us to adapt LLMs using a small external module, so we don't have to fine-tune the whole model. With LoRA tuning, we keep the model weights the same and add trainable low-rank decomposition matrices to each layer as an adapter module. This module has a lot fewer trainable parameters than the full LLM, which makes it quicker and more robust for adapting to new tasks using a small number of examples. So, LoRA tuning is a good way to quickly adapt LLMs for new tasks when we don't have a lot of training data. However, its performance can drop when we have very few examples, like 5 input-output pairs, as we'll show in our experiments later. That's why traditional LoRA methods mainly focus on training and testing within the same tasks, rather than trying to generalize across different tasks with few examples. Section Summary. We consider the problem of adapting large language models, LLMs, to perform new tasks with limited labeled examples. While fine-tuning the entire model based on these examples is inefficient and unstable, we propose a parameter-efficient method called LoRA tuning. This method incorporates trainable low-rank decomposition matrices as adapter modules in each layer of the LLM, allowing for rapid and robust adaptation using minimal examples, making it a resource-efficient technique for few-shot cross-task generalization. Section 3 Methodology. We start our methodology by training LoRA modules on a range of different tasks. To be specific, if we have n different tasks, we train n separate LoRA modules, each one represented as m_i, for the task t_i, in the set of tasks T. Then, for a new task T_prime, that's not in the set T, like Boolean expressions shown in the figure, we use its examples Q to guide the learning process of LoraHub. The learning process of LoraHub consists of two main stages, the compose stage and the adapt stage. In the compose stage, we combine all the available LoRA modules into a single module, which we'll call hat_m. We do this using coefficients w_1, w_2, w_n, so that hat_m equals the sum of each coefficient w_i, multiplied by its corresponding module m_i. Here, each w_i is a weight that can be either positive or negative. In the adapt stage, we merge the combined LoRA module hat_m with the LLM m_theta, and then we evaluate how well it performs on a few examples from the new task T_prime. We then use a gradient-free algorithm to adjust the weights W, which improves hat_m's performance. For example, it reduces the loss. On the few-shot examples Q, after repeating this process k times, we apply the best-performing LoRA module to the LLM m_theta, which gives us the final LLM m_phi, equal to LoRA of m_theta, and hat_m. This final LLM serves as an effectively adjusted model for the new task T_prime, and once it's deployed, we don't update it anymore. 3.1 LoRA tuning on upstream tasks. LoRA is effective at reducing the number of parameters that need to be trained. It does this by breaking down the update of the attention weight matrix of the LLM, represented as W_0, in a space of dimension d by k, into low-rank matrices. More specifically, LoRA shows the updated weight matrix as W_0 plus delta W, which equals W_0 plus the product of A and B here. A is a matrix in a space of dimension d by r and B is a matrix in a space of dimension r by k. Both A and B are new low-rank matrices with rank r, which is a dimension much smaller than either d or k. In this context, the product of A and B defines the LoRA module M, as we explained earlier. By using this low-rank decomposition, LoRA imposes constraints that significantly reduce the number of parameters that need to be trained to adjust the weights of the LLM. Section Summary. The methodology involves training LoRA modules on multiple upstream tasks and then using these modules to synthesize a single module for a new task. The synthesized module is then combined with the LLM and optimized using a gradient-free algorithm to improve its performance on few-shot examples from the new task. This process is iterated multiple times to find the optimum performing LoRA module, which is then applied to the LLM as an effectively adjusted model for the unseen task. LoRA achieves parameter reduction by decomposing the attention weight matrix update of the LLM into low-rank matrices, resulting in a smaller number of trainable parameters. Section 3.2 Compose. Element-wise composition of LoRA modules. In the section titled 3.2 Compose. Element-wise composition of LoRA modules, we discuss how we combine multiple LoRA modules in an element-wise manner. This process involves merging the corresponding parameters of the LoRA modules. However, it's important that the modules we're combining have the same rank R to ensure effective alignment of the structures. To illustrate, if we have a module M_I, that is the product of A_I and B_I, we can represent the combined LoRA module, which we'll call hat M, as the sum of the products of the weights and the A and B parameters. However, we must be cautious. If we try to combine too many LoRA modules at once, we might end up with too many weights to search for. This could destabilize the learning process and prevent us from achieving the best performance. To avoid this, we use a pre-filtering process for the candidate LoRA modules before we combine them. This is similar to the pre-ranking stage used in search engines. In our experiments, we use random selection to reduce the candidate space. We plan to explore more advanced pre-filtering algorithms in the future. In the next section, 3.3 Adapt. Weight optimization via gradient-free methods. We focus on fine-tuning the coefficients W to improve the model's performance on a limited set of examples from a new task. While we could use gradient descent for optimizing W, this would require building a hypernet for all LoRA modules, which would be time-consuming and require a lot of GPU memory. Since W consists of a relatively small number of parameters, we decided to use gradient-free methods for optimization instead. We use a black box optimization technique to find the optimal weights. The optimization process is guided by the cross-entropy loss, with the goal of finding the best set of weights that reduces the loss L on the validation set Q. We also use L1 regularization to penalize the sum of the absolute values of all the WS, which helps prevent extreme values. The final goal of LoraHub is to minimize L plus alpha times the sum of the absolute values of the weights, where alpha is a hyperparameter. We use Shiwa, a combinatorial optimization approach, for the gradient-free methodology. Shiwa provides a variety of algorithms and selects the most suitable optimization algorithm for different situations. In most of our experiments, we mainly use the covariance matrix adaptive evolution strategies, CMAS. This is a stochastic, derivative-free, population-based optimization algorithm that is suitable for a wide range of optimization tasks. It adaptively updates a search distribution, characterized by a covariance matrix. In each iteration, CMAS updates the mean and covariance of the distribution to optimize the target function. We use this algorithm to shape the search space of W, and ultimately select the best weights based on their performance on the few shot examples from the new task. Section Summary. In the compose phase, we combine multiple LoRA modules by integrating their parameters using an element-wise method. However, combining too many modules at once can destabilize the learning process, so we implement a pre-filtering procedure to select the most relevant modules. In the adapt stage, we fine-tune the coefficients of the modules using gradient-free methods instead of gradient descent, as it requires less memory and time. We utilize a black box optimization technique, specifically the covariance matrix adaptive evolution strategies, CMAS, to find the optimal weights that minimize the cross-entropy loss and incorporate L1 regularization. Section 4 Evaluation. In this section, we'll walk you through our main experiments. We'll start by giving you a brief overview of how we set up our experiments and the finer details of our implementation. After that, we'll share our results and provide a brief explanation of what they mean. We used a large language model called FLAN T5 for our experiments. This model is part of a series of models that have similar structures but different sizes. These models are known for their excellent zero-shot and few-shot capabilities, which increase with the size of the model. We specifically focused on the larger FLAN T5 model for our research. Our approach required us to use a collection of LoRA modules that had been trained on previous tasks. To keep things consistent with FLAN, we used the same tasks that were used to train FLAN T5. This meant we included nearly 200 different tasks and their corresponding instructions. We then created several LoRA modules as potential candidates. For each experiment, we randomly picked 20 LoRA modules to consider. We tested our method using the Big Bench Hard (BBH) benchmark, a well-known standard that includes multiple-choice questions from a variety of fields. We used 27 tasks from this benchmark, following the tough guidelines for language models set by earlier researchers. We used exact match M as our measure of success for all tasks. We used the Hugging Face PEFT library to implement LoRA tuning, and we kept the default LoRA tuning hyperparameter at R equals 16. We used the open-source Nevergrad optimization library to implement the gradient-free method, and we made sure that the absolute value of LoRA weights didn't go over 1.5. We started with all LoRA modules having 0 weights. In our standard settings, we allowed a maximum of 40 attempts to calculate the loss on the samples, which we refer to as the maximum step size K. We used 5 examples during optimization, the same number as used in the few-shot in context learning scenario. We set the hyperparameter alpha at 0.05. When it came to the hyperparameters for training candidate LoRA modules, we kept things consistent across all modules. We set the batch size at 64, the learning rate at 1e4, and the number of training epochs at 10. Section Summary. In this section, the authors describe their evaluation process, which involves using the FLON T5 large language model, LLM, and a set of LoRA modules trained on various tasks. They evaluate their method using the Big Bench Hard benchmark, employing 27 tasks and measuring performance using the exact match metric. The implementation details include using the Hugging Face PEFT library for LoRA tuning, the Nevergrad optimization library for the gradient-free method, and specific hyperparameters for training the candidate LoRA modules. Section 4.3 Main Results. Section 4.3 Main Findings. Our experiments, as shown in the table, reveal that our approach is more effective than zero-shot learning and closely matches the performance of in-context learning, ICL, in few-shot scenarios. This conclusion is based on the average results from 5 separate tests. Notably, our model uses the same number of tokens as the zero-shot method, which is significantly less than what ICL uses. Despite occasional variations in performance, our method consistently outperforms zero-shot learning in most cases. Our method's real strength lies in its ability to exceed ICL's best performance, but with fewer tokens. In the world of large language models, LLMs, the length of the input is directly related to the cost of inference. Therefore, our method's ability to use fewer input tokens while achieving top performance becomes increasingly important. Section 5. Analysis. In this part, we conduct a thorough investigation of our method's characteristics and uncover some surprising findings. All analytical experiments are conducted using FLON T5 large. We address several research questions to deepen our understanding of this method. Question: how does our method compare with LoRA tuning and traditional fine-tuning? As shown in the table, we evaluate our method in combination with the few-shot ICL technique. Both yield significant results in the few-shot context, eliminating the need for gradient data. However, a relevant question arises: how does our method, which doesn't require gradients, compare to gradient-dependent methods like LoRA tuning and full fine-tuning? To answer this, we compare our approach, full fine-tuning, and LoRA tuning using 3 typical tasks from the BBH benchmark: binary classification on Boolean expressions, multi-class on date understanding, and text generation for object counting. The comparison shows that our method's relative effectiveness varies across different tasks when compared to gradient-dependent methods. All 3 methods show fluctuations with very few examples, sometimes experiencing a drop in performance despite an increase in the number of samples. Despite these challenges associated with limited data, our method manages to deliver comparable or even better results than its gradient-based counterparts. If given more than 20 examples, our method's performance aligns with that of gradient-focused training, but only in simpler tasks like binary classification. Our method shows significant improvements on complex multi-class classification and generation tasks, although there is still a noticeable performance gap compared to traditional tuning methods when given a sufficient number of examples. Question: which LoRA modules are most effective for BBH tasks? We hypothesized that combining LoRA modules could bring together skills and insights from various specific tasks. To test this, we examined how much influence a single LoRA module had on the 27 tasks from the Big Bench Hard (BBH) benchmark. We measured the impact of each individual task by calculating the average absolute weight. The top 5 tasks, as shown in the table, had a significant influence, as indicated by their high average weights, suggesting that they were particularly effective in transferring skills across tasks. Interestingly, their weight values suggest that these tasks were significantly improved in sequential tasks. A common feature among these top 5 tasks was their inherent need for reading comprehension and reasoning, higher-level skills. Question: how effective is the gradient-free optimization method? To evaluate the accuracy of our gradient-free optimization method in correctly identifying the most suitable LoRA module for a given task, we conducted a study using the Wiki Table Questions (WTQ) dataset. We intentionally included a LoRa module that was specifically trained on the WTQ dataset in our pool of LoRa candidate modules, which originally came from tasks exclusive to the FLAN collection. We then set WTQ as the target task and calculated the weights using the methods used in our learning approach. As a result, the WTQ-specific LoRa module was given the highest weight, demonstrating the algorithm's success in identifying it as the most relevant. Furthermore, the combined LoRa module showed a slight advantage over the WTQ LoRa module. This supports our claim that our proposed method can effectively select the best upstream LoRa for a new task. Section Summary. The experimental data presented in table demonstrates that our method outperforms zero-shot learning and closely resembles the performance of in-context learning, ICL, in few-shot scenarios. Our model achieves this superior efficacy while utilizing an equivalent number of tokens as the zero-shot method and fewer tokens than ICL. Additionally, our method consistently outperforms zero-shot learning and even surpasses ICL at optimum performance, making it more efficient in terms of token usage. Section. Model merging. Our approach is heavily influenced by the idea of LoRa module composition, which is a key area of research in model merging. This field of study can be broadly divided into two main categories based on the ultimate goals of model merging. The first category is about merging complete models. The aim here is to bring together models that have been trained separately in order to achieve the performance benefits of model ensembling or multitask learning. Previous research in this area has often assumed that the models being merged share the same architecture. Some methods merge models by approximating Gaussian posterior distributions derived from Fisher information, while others merge models guided by weights that minimize prediction differences. There are also approaches that merge models with different architectures, for example, by setting the weights of different models before they are merged. Some research in this category merges models that perform different tasks by identifying common features, without the need for additional training. However, our work differs from these in that we focus on merging models to facilitate cross-task generalization. The second category of model merging research is more closely aligned with our work. It originates from a shared interest in module composition. Numerous researchers have contributed to this field. Some have broken down and reassembled modules based on their functionality. Others have suggested controlling model behavior using task vectors. Some have merged modules that are efficient in terms of parameters, weighted according to task similarity. Others have created modules using specific arithmetic operations. Some have improved the performance of unseen tasks. With few examples by pre-training prompts for multiple tasks. Others have averaged adapter weights intended for transfer. Some have focused on learning adapters and a routing function that assigns skills to each task together. And others have focused on merging experts in models that are a mixture of experts. However, these methods generally require multitask training or human prior knowledge on module selection for the downstream task. In contrast, our method does not have any special training requirements and simply uses basic LoRa tuning. Furthermore, the selection of modules for downstream tasks is entirely driven by data, without the need for human prior knowledge. This design has the advantage of making it easy to add new LoRa modules for reuse, allowing our method to flexibly increase the number of potential LoRa module candidates in the future. Section Summary. The section discusses two categories of model merging research. The first category focuses on merging models with shared architectures, while the second category focuses on merging models with different architectures. The author's work falls under the second category, where they propose a method for merging models to enable cross-task generalization without the need for multitask training or human prior knowledge on module selection. Their method, based on LoRa tuning, allows for easy addition of new LoRa modules in the future. Section. Mixture of experts. The mixture of experts, MO, is a method that uses a group of specialized submodules, or experts, each designed to handle different types of data. Each expert is controlled by a unique network that activates based on the specific characteristics of the data it's processing. This network identifies the best experts to handle each piece of data, resulting in better performance than a single, generic model. This method has been very useful in fields like natural language processing and computer vision. Our approach is similar to MO, in that we use pre-trained LoRa modules that can be compared to the experts in MO. However, our method doesn't require any special adjustments to the LoRa's during training, and allows for flexible assembly of LoRa modules at any scale, each tailored to different tasks. In contrast, MO requires a set number of experts during both training and testing. Recent research has shown that using both MO and instruction tuning together can improve the effectiveness of each. Cross-task generalization is a recent development that aims to improve a multitask model's ability to generalize across different tasks, which aligns with our research goals. Among these developments, the connections between CrossFit, Recross, and LoraHub are particularly noteworthy. CrossFit requires a small number of labeled examples of the target task for fine-tuning, but it uses task names as hard prefixes in templates, which can make it difficult for the task to generalize. Recross, on the other hand, doesn't require labels for few-shot examples for retrieval, but it does require a fine-tuning process using the retrieved data, which can be time-consuming. In contrast, LoraHub uses few-shot labeled examples and a process that doesn't require gradients for optimization, allowing for iterative updates of weights to create the LoRA modules. This method is more efficient and cost-effective than previous methods. Overall, LoraHub provides a more practical and feasible solution for the optimization process. Section Summary. The Mixture of Experts, MO, is an ensemble method that uses multiple specialized modules to process different types of input data, resulting in superior performance compared to a single generic model. Our methodology, similar to MO, aligns upstream trained LoRA modules with the expert design of MO, but with the advantage of not requiring specialized manipulation of LoRAs during training. Additionally, recent studies have shown that combining MO with instruction tuning enhances the effectiveness of both approaches. On the other hand, our LoraHub approach offers a more practical and efficient solution to the optimization process compared to other methods like CrossFit and Recross, as it allows for iterative updates of weights using few-shot labeled examples and a gradient-free optimization process.